So today we will be looking further into other more advanced C++ functionality. So we will start a new project for that, and we'll take a look into structured exception handling. So you might remember from the earlier lectures how exceptions work with just C, so they were not particularly flexible. You could cause an exception and you could take an action on it, but it really didn't give you much in the sense of being able to somehow in a controlled way to take decision based on what exception happened, pass more data. You just had an exception code and allocation, so it was a bit difficult if you would want to cause an error message or something that is more directly understandable to the user. So we create a new project, we call it CPP C++ exceptions, and we'll take a look how exceptions work in C++. There they have been greatly enhanced with a lot of functionality. So let's first create some simple function that will be then throwing exceptions for us. So void my error, and let's call it function. Now it doesn't do anything yet. Okay, so the way you throw exceptions in C++ is you are using the throw keyword. And the nice thing is that you can throw pretty much any object as an exception. So you can, of course, in the simplest case, just throw some error code, 0x 1, 2, 3, 4, for example. And if you run it as is, of course, the application will crash. And we have here exception unhandled, and so on and so on. And of course, we get some information like what type and which address the thrown object has. So we get some information. And as you might remember from our C lecture about exceptions, we can catch those exceptions in C. In plain C, we use the try except statement. In C++, it's similar, but it's a try and then a catch. And the thing about the catch is that it takes some sort of argument. In the simplest, most generic case, you can just specify 3 dots, which means catch and everything. And now if we run the application, it won't crash. And of course, as a short reminder how this thing with all these exceptions work, let's print some debug lines. For exception, after and here let's write some start. Before call, after call, and in exception handler, and then of course done. And similarly to normal C exceptions, of course any of those after lines should not be reached. So when we run it, you will see that we start, we enter our try block, we call our function, and we are here before exception, then we throw the exception, and then what happens is we end up directly in the exception handler, where we can do something, we can react to this exception, and then finally, of course, we can continue execution of our parent function as if nothing happened. C++ does not give you the ability to resume. So C is much more low level, and there you really have the option to tell in your exception handler that you want the operation which caused the exception to be retried, basically, which on a low level is might be in certain scenarios useful, but of course on a more higher level is kind of useless because you would never expect a different outcome. With just C, you might have certain scenarios where you want to rewrite the code or do some fancy things, so there might be a use for that. But with C++, you are not doing such things. You are on a higher level of abstraction, and therefore there is no way to resume or rather retry the operation. It just bugs out. And the exceptions in C++, they have quite important behavioral differences. So let's create some object for testing. It's a class C my object. Public, we will give our object a constructor and a destructor. Again, we are lazy, so we are writing everything in the header instead of putting the function separately. Okay, and let's create an instance of the object, maybe here. Actually, let's give it the ability to contain a name, to remember its own name. And it's okay. Char Stern or char name. Let's give it a fixed length. Although no, it's fine if we do it like this. Char const char asterisk np name. So what we'll be doing here, we will be passing a constant pointer to a constant string. Okay, object per name, comma, named %s. Here we have the destructor, and when we create the object here, we can just pass a string, let's say object1. Then we do the same here. We create the object 2. Actually, we don't need to differentiate it here in the file, in the object's name itself. And it will print when it's created, and it will print when it's destructed. So let's run it. And as you see, when the exception happens, I think before it's written with an F. When the exception happens, after it happened, before the exception handler is invoked, our objects which have been created on the stack are destroyed. So in normal C, when we would cause some exception, then we just directly, instantly go to the exception handler, or as instantly as the operating system can facilitate it. It's a bit convoluted since exception handling usually invokes the operating system to handle it. But from the program's perspective, if we take out the things that the operating system has to have to do in such a scenario, it's almost there. It's pretty much direct. And the important thing is that nothing in the state changes. You end up in the exception handler, and everything remains as it was just before the exception happened. Here in C++, this is completely different. As you see on this very simple example, all the objects which have been created within the scopes which are affected by the exception will get gracefully destroyed. So for example, if we would have allocated some memory here somewhere, and then we would have thrown an exception, if we allocate the memory just with a normal pointer or normal C array, then of course it would stay allocated, which would not be good. At some point we would be using all the memory of the system just for garbage. So if you are using an object to hold on to your memory, some sort of smart pointer, which what this is we will take a look on a bit later, or some sort of smart array, as one we already have implemented, I think, during the last lecture in the C++ demo, where we had this array that allowed us to hold on to a value. Those things remain operational even though an exception was thrown, and can do a proper cleanup. We can maybe grab the array. We created it here somewhere. One moment, please. One of the recently, or was it with templates? It was in the templates, I think. Here is our smart array. So we just bring it here, and then of course let's say we allocate some memory inside the function my array, data. We need to specify type, let's say int, 10 elements. Then of course just like the print of the destructor here, when we run it and the exception happens, after it happened we will here end up and clean up the memory. So as you see, the call trajectory goes through quite a few internal functions of the C++ runtime provided by the Visual Studio. If you would be compiling for another platform, like Linux, then you would have some other functions doing in essence similar things by the probably glibc or something that in GCC takes the place of the Visual C runtime. Every C++ compiler will bring some own C runtime, and those are from their behavior compatible. They're not binary compatible, but from the source code side they do the same things. So this is a very important feature that helps you manage resources and ensure that you don't have any resource leaks. Now coming back to the exceptions themselves, you can here, as said, we are catching any exception, but in principle we can differentiate based on what type of exception has been thrown. So for example, here we are throwing an integer, so we could write here int error, and then we could in exception handler, comma, int error or %e, and error too much, and then we can write which error we have received, and when we run it, it will work the same, just that now I should be consistent. So if this is hex, then this should be also hex %x. So we get our error, and of course if we have hex we should prefix this with 0x, because with numbers which don't contain A to F, it's difficult to it's impossible to say whether it's hex or not hex, so you always prefix 0x for clarity. But our exception could throw something else, so we can, for example, give a parameter here, or maybe we just make another function which throws another error. And for example, as an error you could throw a string, and as many exclamation marks as you feel appropriate. Then we need to give it another name, error2. So we comment out our error function, we throw our error2, and now when we run it, the application will crash, because our exception handler is only set up to handle integer exceptions. And of course this works over an arbitrary level of functions, so we could have here void myfunc. We can have this myfunc allocate some object. Okay, let's rename this to object 3, for example. Have another object 3 here. Then we have myfunc, which then will call another function which will cause the exception. We can of course put all the functions here, and we will just then uncomment the one we want, and then this goes here instead. This will behave the same way, just that we have one more object to clean up. We still got the unhandled exception and thus a crash. So if we want to catch this exception, we need to set up a second exception handler statement. So there we are throwing a const char asterisk. And now we can print this instead, %s. And now our application doesn't crash anymore. So as you see, here we just catch this exception, and for any kind of exception you might want to throw, you can set up such a catch handler. Of course, with just string and just a number, this sounds not very flexible. But in fact, you can throw any object as mentioned. So you could, for example, create a completely own exception class. Let's call it class C my exception, and then you can throw something of this type. And let's say it takes a int code and a const char asterisk string. String might be optional. And then of course we would have a or we keep it public with the value, so const char asterisk stir and and a int code. We could in principle initialize it just here like this. But since we only have one constructor, we will be always initializing it the normal way anyways. But let's be consistent here. Let's give this a prefix encode, yeah, so that they have all the same prefixes, and of course a semicolon. So let's create a third function which will throw an exception. My exception 3. And this function instead will throw a my exception. Zack. Oh, actually, let's do it even more funny. So we can have multiple levels of exception handling. So we can let's leave it here. Let's move this up there. We put this in here. We stay with call 2, and here we might make another try. Then we call my function. Zack. Catch. And now we try to catch our exception. Now we have the choice whether I want to throw the exception as an object, is by pointer or by reference. The simpler way is to just do it by reference. So let's do this. My error. Okay. And what we will now do is here inside those two exception handlers, we can throw another exception. My exception, which takes our error code. Oops. And nothing else. We don't have a string, and here since we have a string, but we don't have an error code, we'll say, let's say that's the error 123. The error 0xa or e for exception doesn't matter, and of course the string. So now our function 2 will cause an exception which will be caught in the outer function, which then will be thrown as another exception and caught by our function in the main function. And of course we could add some additional objects and things here to wrap everything any way we want. Object 0 before call, after, and then of course here we would want to catch it in exception handler %error. My oops, e is missing, my error punct code. Sorry, first is string, but string might be null, so let's go with code first. Code. We can we comment those out so that we don't print twice things. Error and comma is the string, and we can also use the trinary operator to ensure we don't try to print something that doesn't exist. Okay, let's run it. And as you see, it works as expected. We get %x. The code was E in this case, and then it writes everything as should, and it calls all the destructors of all the objects before our final exception handler gets invoked. Yeah. So, any questions so far? Okay. If there are no questions, then let's continue. As mentioned, the other way how the exception can be thrown is as the object on the heap, where we just use the new operator. Of course, we need to ensure that the data which we want to contain in our exception are available. So here, in the end, what we are operating is a pointer to the memory here in the function, which is constantly just created and written into our image in memory, and it can be referenced. So it is not created neither on the stack nor on the heap. It is just created in a static part of the application image, which can be addressed as any other memory address. And it is important that if we would have things here on the heap somewhere which would want to try to return within this exception, then those things might end up unrolled, and they will no longer be available for the operation to be performed. So our myString might, in special cases, refer to invalid memory, which would not be good. In which case, for example, here our exception would need to be made such that it makes a copy and keeps the string such that it remains accessible, and then it is disposed once the exception goes out of scope. But of course, here the other way is of course just to use the asterisk, and then we can catch an exception thrown as a new with new. It's called like this. And what we also can maybe do is for the exception, let's add some prints here as well. We won't care for the name because we want to keep it simple. And we add a destructor so that we can observe how the exception's lifetime is. And of course here, where we have our exception, we need to remember to delete it since it was created on the heap now. So let's run it. And as you see, this is the last thing. We are deleting our exception. We can try again our other case. Zack. Here, as you see, the exception also gets so first of all, the exception of course ends up in the upper branch. So let's rerun it again. So we end up here, and once this block goes out of scope, you also see that automatically the destructor for our exception is triggered. But if we would have passed any of those objects to the exception, for example, the object could have been a string, then at this point, of course, as soon as the throw is completed, those objects would no longer be available. It's important to keep in mind, because otherwise, as said, you might run into some issues with your memory management, which would not be, of course, recommended. And last but not least, of course, at the very end, we can have again a catch-all statement that just catches any exception something else failed. Generally, of course, it's not necessarily recommended to use such catch-all statements, because this means that you are kind of not sure what might go wrong in your application. So for example, you would add such things only in a debug build, and then if it happens, then you would have a second breakpoint to investigate what happened or something like that. Some people like to do such things in a release build just for the purpose to not having the application crash. So sometimes some memory leakage is not as bad as having the application crashed. So it will depend on your use case if you want to use such catch-all things. It's important to note also that the way this works here with the types also works with derived types. So you can create, for example, a myGeneric exception class, and then have myString exception and myInteger exception and my something else exception, and then you could either catch on those derived exceptions, or you could also have a catch handler on your abstract exception, which will then react to all the exceptions which have been derived from this. So this is really a very flexible mechanism, allowing to manage exceptions in your applications exceptionally well, pun intended. So when this mechanism and other C mechanisms are used properly, this can be very powerful and quite safe, because as we have seen, we have this automatic unroll. So if you ensure that all the objects and resources you are referring to inside your code are referred in a in a modern way by some wrapper object which is held on the stack, then you can ensure that if you throw an exception, no matter what you have been doing, you will gracefully terminate from this execution path and then enter your exception handler. Without, of course, creating too many samples. This is not super easy to demonstrate. As we have seen with the abstract array, we can unallocate memory automatically, but other use cases would be, for example, releasing file handles, releasing resource handles to some other objects, for example, some device objects provided by a library for some scientific instrument. They usually work the way that you initialize some device object that allows the library to track the state of the device. For you, it is an opaque object. You just know that you have to pass it to certain library functions and which function to use to clean up the object. And you can create a custom object wrapper like we have done here with the template of the array, using templates just not for an array, but just for a single object that will be created and then destroyed using a specified function. So this gives you all these nice possibilities. And once we have taken a look on smart pointers and maybe some more explicit examples of these mechanisms, that will be even more obvious how this all works. At this point, I think with exceptions I have showed you enough, and all the mechanisms, all the important mechanisms of the exception handling should already be demonstrated. So let's proceed to the next interesting thing. That will be operators. So let's minimize all those things and create another project. Zack. New project, console app. So let's create some class. Let's call it CMAC address. So a MAC address is an address used by network equipment to identify a particular device uniquely. It's a 48-bit number, which is a bit odd because 48 bits is not something any CPU would have as a native data type. So if you are on a 32-bit CPU, you need to use either array of just an array of bytes, or you need to use a int32 and an int16 together. Or if you are on a 64-bit system, what you would usually do is you would use a 64-bit variable and then just ignore the top 2 bytes of the array. But for our demonstration purposes, let's say we want to have a object which can store our MAC addresses and which can do this in a way which ensures correctness, meaning, for example, that the top 2 bytes must always be null, and so on and so on. So let's give it a constructor and a destructor. And for the constructor, let's say we want to be able to initialize it from a 64-bit integer. And of course we need something to store the data, as we said. For simplicity, we'll be using a unsigned int64 called data. Okay. And before we take a look on the operators, we will do here already our first sanity check, for which we will need a exception, which we can copy from our exception example. Here we take our myException class. And here we have to check, so if e and 0x ff, if this is not null, then throw. And yeah, as you see, you can throw exceptions from a constructor or a destructor as well. Although no, from a destructor that would not be good, because then you will not do the cleanup properly. But and it's not customary to do so. But from constructors, it's quite customary to throw exceptions. For example, if you fail to allocate some memory, which you need for your object to operate, you would just throw an exception, insufficient resources or something similar, which would then abort whatever procedure you were inside, and then ideally, if everything is implemented correctly, gracefully clean up whatever has been already partially allocated. But here we just throw our exception, and on x1 0 0 0, let's say code 1, we give it a message string. We just call it invalid parameter. We will not be wasting our time to find out some nice messages. Then of course we want to be able somehow to read the address, so let's make a 64. Actually, what we also could do is we could create a struct for that. As let's go with unsigned. Let's go with unsigned char. Our value 6, and that's that. And here for simplicity we could pack the whole thing in a union. Union e64 or type make data, or let's call it and here will be this should not be called value, because that will be a bit boring. Let's call it bytes. Yeah, you could of course also define it as a const array, but it's nicer to wrap it in something. And now, since this is a union, of course, when we can assign either of them, and both will, since they share the memory, but that will not be correct, it will be shifted, so we need to do it like this. Or alternatively, what we also could do is we could put a structure in another structure. And I think if we don't give a name to the outer structure, we should still be able to refer to it in a nice way. Yeah, we can still refer to this as data. Nice. Okay, and then of course something to get. So let's say const. Or let's not go with const. Let's just return the thing as a copy. So we could. There are two ways how you can return objects. You can either return them, or generally return things. You can either return them as a copy of something, or as a reference to something. Returning as a reference means, of course, that we then need to ensure that this object remains valid, and this is something that's like you need to do it manually. The compiler will not do it for you. So it is, if you can afford it, the safer option to just return a copy. and I get let's call it get Mac, which just returns value.data, and we could also have a in64 on site in64, of course. Get int, which will return value, the typo. Now this will be working. It's just breaking because here we have not completed our statement. Once we complete this, it is all fine again. Right. And at this point, we would probably also want a set function. So void set and at this point we can improve this. We can grab that, put this to our set function, and from our constructor just call set on our e64. Okay, that makes it more elegant. And then the way that the general idea simply is that we can now pass create objects which can hold our MAC address. Oops, MAC. We can also start with an empty object. We have not initialized anything, so we need to initialize this as 0. And then we set something. Let's say 0x. And if we set something valid, it will be fine. If we set something invalid, it will not be fine. And what we might want to do with such numbers, for example, we might want to do some operations on them mathematically. So, for example, if you would have something that, let's say, emulates network cards, and then you just specify the first address, and all the other cards will get like an address incremented by 1. There you would want simply to be able to make a +1. Of course, you could just get the value here, do a +1, and then set it again, but that would be kind of cumbersome. So what we can do is in C in C++ is that we can specify custom operators which work, so to say, in place of the normal operator. So let's say we create 2 MAC numbers, MAC addresses. Usually we would not, that is too long. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. That's what that was already an invalid number. Oops. Or let's start. Let's say we want to add those two. So, and this needs to, of course, have a different name. So it would be our MAC3. We would want this to be MAC plus MAC2. And as you see, of course, the compiler doesn't like that because it doesn't know what plus means for such a strange object. The compiler knows what plus means for an integer or for a double, but it has no idea what it means for our C MAC address. But we can tell it what it means. We can create a operator which will implement the plus operation. So usually operators return either a copy or a reference on themselves. So for a plus operator, it's a copy, and pretty much it's just a function which is called operator with the right value, and then it takes as an argument a reference to the other objects. Of course, we can call it any way we want. It does something. And then it returns asterisk this. And I think I skipped this during here. Yeah, I did. So, as you might remember from our earlier lecture, inside our objects, inside any object, we can refer to the variables we have directly. but there might also be a use case where we want to refer to ourselves for some reason. Basically, where inside a function we want to get the address of the object inside which we are executing, and this can be done using the this keyword. The this keyword is kind of a virtual variable which exists on any object, and it allows you to access the object as if you would access it from the outside. So for example, if you make this arrow, you get again access to all those things that you have here that you would have access if you would normally use the arrow operator on the object outside. And you can use this directly to get the address. And if you need the current object to be present not as a pointer, but as a as something that is concrete, then you can use the asterisk to dereference the current object, and then you can access it directly. For example, if you want to oh, we have a typo. If you want to return a copy, you could do it like this. As you know, with integers, we would just return asterisk pointer to an integer if we want to its value, and the same thing applies here. Although this, of course, again gets a bit complicated because how you make a copy of something, right? This is not necessarily intuitive to the compiler. In this case, the compiler implements its own assumption, because like for plus, it's extremely ambiguous. It can do anything basically, especially if you have some many member variables, etc. But for just copy, in the simplest case, you just want to make a copy of the memory of the whole object, and that's it. And thus, since this sort of operations is can be assumed, the compiler will automatically generate you a set of operators which will allow you to make copies of objects. So here, this works. Of course, we still need to implement the plus. So let's do that. So on our current object, this comma I plus equals our other thingy, and we have implemented it. And of course, to be more useful with the use case we mentioned, you would rather want something that takes an int or a int64 and then use this for an operation, which you can do. So you can define operators for different data types. So you can, if you would have a string object, which we will take a look on a bit later, then for example you could define an operator on your string object which would allow you to plus a number to the string. Usually, of course, this would mean, usually with strings, the plus operator means a concatenate, i.e. append whatever you are plussing, let's call it this way, to the end of the string. And in case, of course, of an integer, you would want to first convert the integer to a string and then append the existing string. So you could create such operators which do whatever you need. And of course, you could also have here another complex object with some other meaning. For networks, you could have some object that takes some network mask and does some operation on it, etc. Usually, of course, then you would probably use something like an or an and or something of the sort. You would not use the plus. That doesn't seem intuitive. But as said, you can pretty much use here any operator, not just plus, but you can use a multiply, divide, modulo operation, whatever you want. You can also use this to create this plus equals operator. So for example, if we want to have here our Mach4, which starts just as Mach, and then we want, oops, plus equals 3. Again, we don't have this operator, but we can create it. So let's copy this one, make this plus equals, and this thing wants to return usually a reference, because the plus equals changes the object. So here, yeah, and here we have already the first bug, since we should return a new object here. So we should use address Mach is equals asterisk this. Then on that thing we do the plus equals, and then return the thing. Yeah. Or the other way we could do the same thing actually is could use our constructor here. Since we are returning copies, we can do it like this. We take our value punct e plus other. So this is mostly similar, just that here of course we have a different source for our addition operation, but in principle we could also turn the upper one into a one-liner, and then we return a copy, and then here, since this one modifies ourselves, we actually modify ourselves and return a reference to ourselves, and here we forgot a bracket. And of course another thing you might want to do is you might want to check if Mac2 is equals Mac4, and if it is, do something. Now you could in principle say that if you don't have an operator, the compiler should just do something that makes a memcmp on the data on the memory, but this might be often wrong, so the compiler doesn't make any assumptions, and it tells you that if you want to compare two objects which it doesn't know, you need to define a compare operator. So this has a boolean as a return value, and it's an operator equals equals. You could also have unequals and so on. And of course it's as simple as it gets. This m value e equals other punct m value punct e. So it's trivial, but it works. And of course for the non-equals operator we can either implement it again, or we can use negation. I mean, this is kind of the less efficient way. Asterisk this is so not asterisk this is equals other. Oops. So because here when we do it this way, you have like one more function call, but depending on the complexity of this thing, it might be either still worth it just because you then save memory, or if it's something trivial, then the compiler, if you build a release build, will optimize this away and just make a copy for you. So depending on what is more efficient. And there is also another strategy how you can implement such operators. Is you provide a function, let's say int compare. Also operators which don't change the current object should be const, so that we can execute them on const members. Yeah, so this one is not const because it changes, but this one and this one can be const. Right, and here we make a compare which takes again an other, and it's const. And the idea is that the compare function will return 0 on match, greater 0 if one is greater than the other, and less than 0 in the opposite case. And we could, for example, use the mmcmp function, which does exactly this, just with two memory buffers, and we will feed it value punct data punct bytes and other punct value punct data punct bytes, and we need to specify the length of memory to compare. We know it's 6, so we write 6. We could of course try to be even more correct, and we make a define def maclen is 6, and then we will use this instead of 6, so that we can be always sure that if for whatever reason we would want to change this, that this will remain consistent. Although of course then here we would kind of need to change the length here as well potentially, so it's still a more correct approach. So return memcmp, and then okay, let's turn those into one-liners. And comment them out. Now we have just before we comment them out, we copy them. So here we just return compare other. So equals, so it must be equals 0. Here of course is not 0. And if you would want to check whether it's greater or less than or something, we can do the same thing. So greater equals or just greater, less than equals or just less than, and then we of course just here applied the same operators on the 0 as the comparand. And depending on what we want to do, and usually you can somehow break down your object to a comparison of memory. Usually if you have things which are supposed to be comparable, if you have objects which are more complex, then usually you would also not want to create any hierarchy between them, like what is greater than what, because they probably would not be suitable for some sorting operation anyways. But for example, with network addresses, this is something we might want to do, and we might want to check which one is greater, especially if you would want to check, for example, if some address is within a range of addresses, then it's quite obvious that you need exactly those operations. And let's be honest, we probably will not need this one, so let's comment it out. We only will need like to add a number and of course subtract a number if we want to walk around in the address space. So we just change this to minus equals. We don't need any multiplication or division, that would not make any sense. We could maybe use some or AND operator to make some operations with network masks, but sorry. But for MAC addresses you don't do that. You usually would do this with IPv6 v4 addresses. Even with IPv6 addresses, the way they are managed is slightly different, so you don't usually use a network mask. You only have some network suffix instead that defines you the range to which network those addresses belong to. So as you see, for example, using such operators, you could implement an own integer, for example, one which is bigger than what the computer would be able to handle. So for example, in cryptography, you are using very large integer numbers, and since of course no CPU can handle them natively, unless it's some sort of exotic cryptographic coprocessor which is explicitly made for this one application, but any general purpose CPU will not be handling a kilobit large numbers or 4 kilobit large numbers or whatever else you need for RSA to be at least remotely secure. So what you would do is you would create your own class, which then would emulate using operations on smaller chunks all the functions that you need to have a full integer with all the multiply, divide, modulo, etc. operations. And as already mentioned, you could also use operators on a string. So for example, with strings you might want to use the AND operator to concatenate strings, or you would want to use the plus operator, minus kind of, and the other ones don't really make sense for strings, but it's somewhat nice to be able to plus together strings quickly instead of using some append function. It's more elegant. So if you would ever implement your own string class, then one of the operators you would definitely implement would be some sort of concatenation operator, for which you would use either plus or AND. You could of course use something else from the characters which are allowed for operators, but that of course would make your code rather confusing for others to read, so it's rather not recommended. Okay, so right, this functionality we have removed, so let's +5. Yeah, let's do it like this. And as mentioned, the compiler will generate automatically assignment operators, but for completeness, let's create them here manually as well. Operator. So an assignment operator, since it changes, ourselves will of course return a reference. Operator is equals. It takes something else. Oops, not this type of something else. This type of something else. and then this value is equals, since those operators are created automatically, we can do it like this. And return the reference. Another use case for manually defining an assignment operator is if you would want, since by default you can assign objects to each other, and this might not necessarily be desirable, you can put an operator into a private section or a protected section. And if you do this, then the operator will not be callable from the outside, so it will cause a compiler error when you try to use it. Although here we have not been using it in a way that would trigger it, I think, because there is a second thing. It's called a okay, here it already we already defined it. We'll make a copy. I made the copy, so I wanted to move it. So the thing is, there is a second mechanism to assign values, which we actually are using here. So in this line you are using the equal sign, but what you're really doing is you are using a special constructor which was created for us as well by the compiler. So to trigger our commented out assignment operator, we need to make it explicit. So here, as you see now, it says that it is inaccessible. So in principle, the thing could be completely empty. We just want to somehow mark for the compiler that it is not available. And of course, as soon as we move it back to somewhere where it is accessible. So first of all, here, if it's not defined, it works because it creates it by default an own interpretation of what it should be. But if we create it here explicitly, then our will take precedence and there won't be a built-in one created. And if you want to see what is here happening, why this works even if this is not accessible, the reason is there is by default a copy constructor created, which is this thingy. And again, this will in the end just behave the same way. So when we can, for example, have here, oops, let's put some breakpoints and then step through everything. So we have Mac. Let's say we say it's Mac free, and then we change our mind. That makes sense. Okay, so we broke something. Oh, we passed in. Oh, sure, I passed in invalid value. We're already running our safety check. And to be honest, actually, of course, we should do this for all the operations which might change it. So let's make a protected function void validate, which will be responsible for throwing exceptions if the value becomes invalid. And then we'll always just invoke validate whenever we change it. So of course here, but after the assignment, and then here after those operations we will validate the result and throw an exception if something bad happened. Right, so we are at our right, and I didn't fix this is not valid. We need the first ones to be 0, so let's say we'll take something like this for our values. That should be valid enough. Okay, and here if we step in, then we end up here in this copy constructor, even though we actually used here the assignment operator. And then of course when we step out and then go to the actual assignment, then we will end up in the actual assignment operator because the thing already was constructed. And there is another sort of operator, by the way, which is of constructor, which is worth mentioning. It's the move constructor. It looks like this, so you use like a double end, strangely enough. And the purpose of this thing is that if you would have an object which holds some internal state, something that is not part of the object's own memory, but for example, if we would have a string, then we would have some array of characters, and when you have a function that works with some data type and then returns this data type as a return value, you can use such a move operator. So it will be if present invoked by the compiler, and then the idea is that you move the internal object from whatever variable you are returning to the variable's memory to which you are returning it, instead of doing like the thing on foot by creating a full copy, a deep copy, and then releasing your own object, which kind of is wasteful. So we could extend this sample in a way such that we can take a look on how this works maybe a bit later. But it's just important to say. And of course, what you would then do is somehow you would invalidate the old reference. Here, of course, it's not necessary. Why doesn't this? Right, value doesn't take 0 value, like this. But because so if this is part just of the memory, then it kind of doesn't matter. But if this would be a pointer, then we would need to want to ensure, because after this operator was called on the other object as part of the return process, its destructor will be called. So if its destructor would then try to deallocate the object, then of course, since if we would be sharing the object, then it would have gone away. So we need to invalidate the reference such that the object really is moved from one variable holding it to the other. And usually you cannot invoke this thing like explicitly. It is just an implicitly if you are returning something. Okay, so this much to the operators. Okay, good. So any questions at this point? Okay. If there are no questions, then let's proceed. So we were here, so let's run it again. So again, our plus something operator will bring us to the plus operator, and our compare operator will again invoke our compare operation. So really it's a kind of just an aliasing of functions, because it's like not some completely different language construct. It is just a function with a predefined prototype, and then it can be used in a simple way in equation. So this is quite useful, as mentioned, for creating at least certain classes of own types. And there are other operators which are then again useful with other types. So when we return, for example, here to our array, let's grab it and add it here somewhere. So this array, while it does array stuff, it allows you to set something and get something. It fails in a very important way as an array, because normally if you create an array, let's say of int, my array m, and for int e equals 0, e is less than count e plus plus. My array is complaining. Alright, it wants the amount of elements. Let's say 10. Right, so what we would want to do with an array is you would want to, for example, do this. And our array cannot do it. Actually, the compiler here does not yet complain, but once we start trying to build it, it will complain that there is no operator square bracket, which is kind of annoying. Of course, we could, instead of doing this, write like something, I don't know, set at e comma rand, but this is meh. It's not what we would usually want. And there are use cases. So with a normal C array, of course, if you use the square bracket operator, you can use the AND operator before that, and this gives you a pointer to this element in the array, and then you can do things with this pointer, and you don't need to like explicitly assign it later on, because you are working directly on the array pointer. Very nice, very powerful, and with our array as is, very impossible. So we need to extend our array using our knowledge of operators. We will add to it the square bracket operator, which can can either return t or t reference. We will want to, of course, to use t reference since we want it to be assignable. If it would be just t, then we could not assign anything to it. Operator, square bracket, int index. And the funny thing is that this thing here, it doesn't only take integers or size t or, well, a number, but you could create a square bracket operator that takes, for example, a string, a char, anything you want. And then it would be, of course, up to you to give it meaning inside of your object. So, for example, you could create a map or a associative array where you can store key and value pairs, and then you could access those values using the square bracket operator and providing the key string as string. So this is something we'll take a look on later today. But here, in this case, the thing is as trivial as can be. We just grab our get at. Right, and here this kind of, we cannot do this because we cannot, I mean, as I mentioned earlier in the last lecture when talking about templates, I think I said that it's kind of difficult to work with templates because the IntelliSense is kind of buggy, or rather not functional at all. So even though this, if it wouldn't be a template, would error out instantly, you would see a red underscore. Since it is a template and the thing doesn't know really what it will be until it becomes something, i.e. gets specialized, you only get the error when trying to compile it. In this case, it just tells you that it cannot convert an integer, because, well, t is in this case an integer, to a reference to t, because that would not be valid. So again, we come back to our exception. In such a scenario, there is another way we could have handled it, but the proper way is just throw exception. Let's call it 0x123 exception number 2. I think we used 1 for invalid parameter. Yeah, 2. It's always good to have some exception number. The messages are rather secondary. Index out of bounds. And to be honest, we should also check if this is so greater equals, yeah, or if index is less than 0. Since we use here int and not size t, it could be less than 0, but actually we probably just should use size t, then it cannot become negative at all. So let's do it like this, and then of course we get here a exception thrown, and this is basically like the core thing that makes C++ much safer than C, because in C we would just try to access invalid memory, while in C++, if we are using a proper wrapping object for our raw memory, the object will validate every access. Now there are still, of course, situations where the thing would be problematic. If we take a pointer to the value at this offset and then increment it ourselves, then we are bypassing this safety mechanism, obviously. So we might not want to do it, and there are ways to make it, if not impossible, at least more difficult, but that's maybe something that we'll take a look on later. For now we need to hurry up a bit, so we won't go into all these more advanced use cases just now. But long story short, we just do this, and then we have here our operator. Now if we try to compile it, it will compile and operate. Since we don't print anything, it just silently says all fine. But as you have seen, if you would, for example, here use the wrong value, let's say 11, normal C, as you remember, would just run and be fine with it. Our C++ triggers our exception, and we have prevented successfully any memory corruption. Instead we crash the application, where again we would have some try-catch block around this, so that we can unwind whatever was being done and hopefully end up in a consistent state, allowing the application to continue execution. So for example, if this would be something that is triggered when you press a button in a UI, ideally you could have a set of exception handlers for inside the function which is triggered when the button is pressed, such that basically if it crashes you can display an error message to the user, and from the application standpoint it would be as if the button would never have been pressed. So the states would be rolled back and the application would be in the state it was before the button was pressed. Okay, and of course let's return to our correct case. So these are the other types of operators, and of course there are more, even more operators which one could create. So I mentioned, for example, earlier already a smart pointers, and that would be the next use case for such operators, that we could create something that behaves like a pointer, looks like a pointer, but is smart, meaning it manages the memory for us. So let's do that. We did this as class. Again, let's copy at least something. So obviously a smart pointer makes all sense to be a template, so we call it my pointer. And our smart pointer needs somehow to be initialized, so ideally it will take a actual raw pointer to t asterisk. Actually, we could try to do it in a more advanced way. So, and yeah, we need just a pointer, then we need a distractor, obviously. Then we need some protected stuff. This will be t asterisk mptr, so our actual pointer value. And but let's, for simplicity, make first a simple pointer. So it just takes ptr and ptr is equals ptr. And of course, the most important idea is that we delete our pointer once this thing here goes out of scope. So the simplest way of using our pointer would be, of course, we create a pointer, new, no integer. Actually, let's go with our object. Let's create a MAC address, new MAC address. Argument list is missing. This is not smart enough. So there are two ways we can fix this. So first of all, we can just specify the type. Then it's happy. The other way, the modern way, because it's kind of boring, because you have the information here. You should be able to look on it and know which type the thing is, or rather the compiler should. And in fact, if the compiler is new enough, it can. Just that by default it's not. So we switch here. Wait, let's go for all projects and all configurations. We switch here the standard to C. I think C17. Oops, that's one too much. I think C17 is the one we need. Yeah. And if you use the C++ 2017 standard, in such scenarios, the compiler is now smart enough to implicitly infer which type the pointer will be. Later. Right. And of course, if our pointer is now in some scope, then once we get out of scope, it will automatically trigger destruction. As we have seen with the exceptions, if we would throw an exception, then this also would be properly cleaned up. And this is kind of what makes a smart pointer smart. But of course, we would want to use the pointer whenever possible as a pointer. So for example, we would have a function here, void get local, let's call it get local mac, which takes, let's be smart about it, let's say it takes a smart pointer. Here it won't be able to infer the type, so we need to specify it. What we also could do, actually, instead of specifying it, is type def, just type def ourselves, say pointer type, like this. And what I like to do with those is to pass them as const reference. That saves a little. And then this thing, let's say the job of this function is to assign the local network card's MAC address to our pointer. But, well, how do we do it? Oops. We have this thing here. When we dot, we only have the destructor. When we arrow, we have nothing. We know it holds an object, but the object is private. Of course, the dummy approach would be to kind of expose it with a get function, which, sure, why not? It's sometimes useful to be able to get a, oops, that's the wrong one, get the raw pointer out of a smart pointer. So we could, at this point, dot it, but it's const, so this needs to be const. But this is fine, we are not changing the pointer, we're only getting it. Although, nominally, if you have a const function returning a pointer something internally, you should return it as a const pointer. That would be the responsible thing to do, but in this case, we don't want that. and then on the pointer we could then we have a set. We have a set. We called it just set, but we might want to call it doesn't matter. Doesn't matter. Let's just keep it at set. And then let's say our local MAC address is 0.1234 and then 1, 2, 3, 4, 5, 6, 7, 8. A, B, C, D. Did I lost count already? Suck. It should not. Yeah, that's the maximal length we can fit in. But this is kind of well cumbersome. Always get and then the arrow. That's meh. It's not user friendly. Plus, most important, if you would have some code, some larger code block, which is using pointers, updating it to use a smart pointer would be a huge pain. So of course we don't want that. What we do is again we use an operator. D asterisk operator arrow, and this thing just works as our get thingy. Just returns the pointer. So it's kind of a very boring operator, but it allows us to do something really awesome, because before the arrow why is that not working? They should be working in PTR. That needs to be const. The arrow operator before on our, so like again let's comment this out. The arrow operator doesn't give us anything. It's dead. It doesn't exist technically. It's not even dead. It never existed. It was never alive. But if we create it, then we get it. And the nice thing is, it directly arrows us our object which our smart pointer is holding. We don't need some intermediate step, but we can make an object on the stack, which can be as complex as we want it, to look for, from the perspective of the source code, like a box standard simple pointer. Meaning we can very easily update any code that uses pointers to use smart pointers instead. And in principle, such a pointer, so on a normal pointer you can use plus plus and minus minus and stuff like that too. So pointer arithmetics, as you might remember from our lecture about memory management. Here we have not implemented plus plus and minus minus operators, so our smart pointer does not allow for this. But we could create a smart pointer type which would hold an array and allow. So actually on this array here we could implement an arrow operator and a plus plus and minus minus operator, such that we can make this array behave like a pointer and then access all the inner elements. But we won't do that for now. Here it's only important to do this. And of course what we also could do is we could define other operators. So for example we could define again t asterisk operator end const, which would again just give us the return value. Usually of course when you would make an end on a pointer, you would get the address of the pointer, which would allow you to change the pointer. So if you want to be correct, we would actually need to do it like this. But depending on your use case, you might want your pointer to return only the value it points to and not the value it holds the value. So this would be depending on what you want to do, how you implement your AND operator. And in principle, what you also can do, what would be useful in certain scenarios. So if our pointer would hold something that can be assigned, or actually it can be assigned, so let's do that. So let's say we make a MAC address, my MAC or local MAC. Local MAC is equals, not is equals, is just initialized from this. And then we want, so if this would be an integer pointer, I would write asterisk this is equals MAC. That kind of doesn't work because there is no asterisk operator. So we simply quickly make one. So an asterisk operator gives us a dereference. And that's how it should work. And then voila, here we can make it behave. So as you see, we can, if we complete everything, we can really make this behave like a completely normal pointer with all its normal features. But let's think about error handling. So here we have a pointer. We passed the pointer to a function. Actually, we didn't. Let's do that quickly. which holds something, which is good because it will work. But we could of course try to break things on purpose and use an empty pointer, not assign any value to it. Actually it complains because here we didn't gave it a default value, but realistically you would want the thing to have some null in null ptr some null implementation, so that you can create those things without giving them a value. There are languages like Rust where this is explicitly not desired and not allowed. You cannot make a null pointer in Rust, which kind of makes things safer, but then it makes other things less convenient. So being able to have a null pointer which just defines that there's an object, that there is no object, but you can return a null pointer, that is very convenient. So here we have our null pointer, and then when we try this assignment, the thing will crash. Probably very hard. Let's see. Yeah, it crashed here inside our assignment operator because this is null. But this is like the positive case that it crashed. It is not necessarily guaranteed that it might crash. In special cases, you could assign allocate memory at an address close to 0, and then if your object is larger than even though this is 0, this plus offset of value, I mean, in this case, offset of value is 0 because it's not a virtual function. But if it would be a more complex object, then your value might be some kilobytes further down inside your object, and then this would not even be null, so you couldn't necessarily spot that it's invalid. It would not be that apparent. So what you would want, for example, if you would do something that implies an operation, like this and the other function, this function and that function, you could check if this thing is actually valid, if this thing exists, and then actually if it doesn't exist, throw our nice own exception type, or you can throw a 0 or something. Just as long as you crash the application reproducibly and reliably, it's fine. 0x0003 null pointer exceptions suck. And for the other case, we also need the same safe case. For get, we don't, because if we are wanting to get the pointer, we might want to check whether it's null and other things. But of course, talking about null, we might not necessarily want to crash the application. So let's say the thing is has a return value, and and it tells us whether it was successful or not, and it can validate the parameters it got. So for example, if you would pass a pointer to a normal function in C, you would want to if exclamation mark this thing, then return false. But as you see here, again, it doesn't work because there is no operator for it, and for this we need another operator. What was the syntax for that? I think it was like this. So we can use any type as operator, and then our object will become castable to this type. So before we do this, let's say we have here our MAC address +3, and we want unsigned int64 my int. We want to do this, and obviously it doesn't work. So we can, since our MAC is in principle from the type compatible in some way with an integer, we can create here a cast operator, which just will return m value this should be operator first. M value punct int64, and it should be constant, of course. And voila, this should now where the plus, we broke the plus for whatever reason, but this line works now fine. Why did we break the plus? Because we made something ambiguous, I guess. Yeah, now it has more than one plus which matches this operation. And it doesn't like that. So let's comment it out. We didn't want this in the first place. But the general idea is if you would have an object where you would want to be able to make it assignable, you could. And what we actually wanted to do is here with our operator here is that you want to return basically if this is null or not. So it should return true if this is not. Oops. Yeah. And now of course this thing should no longer complain. Operator ball const, because this thing is const. Yeah, now it doesn't complain. So our pointer becomes more and more like a real pointer. We can now even check with if it's null or not. Before we would need like to get it and check it. That would kind of be not ideal. So we can basically hide away the dangerous parts of C++ in our own wrapper objects as deep as we want and as safely as we want. And this is pretty much one of the most powerful aspects of C++ that we are not bound to what the language comes with, like with pretty much any other language. We can of course to some extent within any language write our own libraries and things, and in some languages you can even with quite flexibly extend objects, but generally especially in more strict languages you cannot do any of those things. But C, even though it is a strongly typed language, allows you to do all these nice machinations with your own objects that replace functionality of the default language and so on and so on. So we have created here, I think we went through all the, or at least most of the useful operators that one might ever want to use. Are there any questions? No questions? Okay. So since we are done with the operators, let's take a look on some practical use case where such operators and templates, which we learned in the last lecture, would be used. Let's create a new project. STL stands for Standard Template Library, and it is a very important part of C++. And strangely enough, it was not part of the very first C++. So initially you had just C and C++ compilers, but you needed, if you wanted to do something interesting with C++, for pretty much anything, some sort of third-party library. And historically, the first Visual C++ compilers from Microsoft came with a set of libraries called the MFC, Microsoft Founded Class Libraries, which were quite popular in the last century, in the last millennium. But as time progressed and Linux also started to become more mainstream, of course, people wanted to have something that can be used across platforms, something that gives you, that extends C++, because as said, C++ as it is itself is very, very bare bones. You can create objects, you can create very complex objects, but you have to do it. You have to do all of it. And if you want to have a simple thing as a string, strings are obviously very useful because you need to pass user entry. You want to create messages for the users. You might to read text files or write text files, process command line arguments. Strings are extremely useful for many things. And in C and C++, without any libraries, you only have the normal length limited C string, which is very not user friendly, as we have seen in our lecture about those things. So more or less the first thing anyone who would be using C++ would want to create is some sort of own string class, which allows you to concatenate strings which have no length limit, meaning internally it will, when needed, reallocate memory, and just for you it is transparent. It starts with some size, you append your parts of your message, you append some more, and at some point you exceed the length, and instead of crashing the application or other bad things happening, the thing just allocates a bigger chunk of memory, copies everything over, disposes of the old memory, and continues business as usual. And Other things, of course, you might want is like lists, as we have written one, for example, ourselves recently, and it was then assigned to you to create a C++ version of the list. These are very useful things, and we have seen already smart pointers now, and in the array that we have implemented in the last and extended in this lecture. So there are really many things which are quite useful, which usually you would not necessarily want to write each time from scratch whenever you start a new C project. Or if you would need some external libraries, then of course some would have one version, another one would have another version, some libraries would be incompatible. It would be a mess. So long time ago, people came together and created the standard template library, which extends C++ with all the nice things that everyone always wanted to have. And while initially the earlier versions of the standard template library were mostly really just fully template oriented, so container type, string type, stuff like that, the more recent versions of the standard template library started including also functionality which is more related to interacting with the operating system than just concerned with doing things on stuff within your application. So already the very first versions of the STL had things like that allowed you to write to, for example, the console, so just write text to the screen or read text from the screen. But it's were very basic text. You didn't have any means to, for example, start another thread or some synchronization objects, or even reading and writing files was not there from the get-go. For this, you would need to use the standard stdlib C functions and so on. But with the later versions, you got file system support, you got multi-threading support, you got a huge amount of very powerful implementations that inside this standard template library then are implemented for every platform individually. So like the old STL versions that you might run across, they would be kind of platform agnostic. As long as you have a C++ compiler that supports the sufficiently new standard, the template library would compile just fine. But nowadays, with these extensions which are operating system specific, for example, Visual C++ will come with an own STL implementation for those functions. So on Windows, you're opening files differently than, for example, on Linux. You create threads differently, etc. So all those things will be done the Windows way inside the library, but the API for the library user will be the same, no matter whether you are using Visual C++ or GCC. GCC will have an own STL implementation which will do the same things, but in the Linux way under the hood. Just the difference is that you cannot take like the GCC STL and compile it with MSVC. That would not work, because it's it's the wrong operating system, obviously. And with the very old STL libraries, as mentioned, this was not the case. They were really completely generic. But this changed, and this is not necessarily bad. So now we will be taking a look in just a few of those objects and types that the standard template library offers, which are the most useful. So as already mentioned, obviously the most useful of all is the string. You need to include the string headers, then you can start using it. Everything in the STL library is confined in an own namespace. So whenever wanting to use something from it, we need to write std for standard and then double point, and then we can use the objects which have been defined in this namespace. Just if you wonder how namespaces can be used, I don't think I showed this. But it is quite simple. You just create a namespace. Was it begin namespace? No, I think it was just namespace. Let's call it test. Oops. And then let's create here a struct. My test. Test. And without the namespace, you could just access test directly. Test something, but since it is in a namespace, you cannot. So what you need to do is you need to take the namespace name, prefix it to your thing, and then you can create something from this namespace. So that's how namespaces work. It's just a means of separating literally the namespaces from each other. So you might, for example, want to have a function which is just called write function, or a class that is called just map, and you might have a certain scenario where you might want to use this keyword for something else. So if you create a very large framework, it is not wrong to put it in an own namespace, like here done with this example. And then of course in the STL everything is in the std namespace. So you have here very many things, but let's start with string, which is a ASCII string, so it's a normal string. You can assign directly a C string to it, and the other type of string is a V string. What's the string? No, V string, which is a write string to which you can assign something that is Unicode. Usually, of course, for anything that is concerned with user input or file names, you would want to use Unicode. For things where you are handling some internal commands or something that you know is not Unicode, it's fine to use the other string. And the nice thing, as mentioned, about those strings, let's just call this just string, is that it has operators defined, like plus plus. You can add more characters to it, or you can get a substring. It's a function, so substring takes an offset. Let's say we wanted offset 1 and we want 3 characters, and we of course have also an assign operator, so we can create another string, substring, like this. So this will end up with 2, 3, 4, and if you want, you can remove things, erase. Let's say you want to remove the first 2 characters. So the string will then end up being 3, 4, 5, 6, and so on and so on. So as you see, it's extremely useful. And of course, in other languages, you would have such things like strings kind of as a part of what the compiler knows and understands. With C and C++, it is really quite peculiar, because except very special exceptions, the compiler as such doesn't know a single class, doesn't know any single function. It only allows you to write those, to create those, and if you have a compiler, then you have your header files which you need to include, and then when you look at the header files to those, you would either get source code for the functions used there, or more commonly you would just get library files. And then if you look into these library files, they will contain those functions, but it will be all external to the compiler. It will not be part of the it will be part of the package, but not part of the compiler binary itself. So for example, on Windows, you can in fact disable all the standard libraries, and then you pretty much cannot do anything in your program unless you write this by hand, starting with very basic primitives. So usually you would need at least one library that allows you to issue system calls to the Windows operating system, and then like the NTDLL, and then from this you could then start implementing all the other things you might want to use. But in principle, you could also just add an assembler file to your C or C++ project and write directly assembler which executes syscalls by hand. Obviously that is not recommended unless you need to, but and we will not be doing this during this lecture, so this is about C and C++, not about assembler. I just wanted to have to mention this, that if you need to do something in assembler, some exotic manipulation of something, you can just add an assembler file to your project and create by hand a function in assembler inside of your ASM file, and then call this function from your C or C++ project completely normally without any complications. And in fact, that for pretty much any function, this is in the end how the function has been implemented for your for the libraries that are given to you. Okay, so we of course had the string. Then of course, as I mentioned, you can print things to the console. You can use std cout. I think we need to include for that the IOStream header. stream, so we can print our string. We can't, but we can print a C string. It doesn't like it. Why? Typos everywhere. Yeah. So again, this thing, for example, is an somewhere implemented an operator. So in the object, so whatever we want to print to the console, let's say a number or a string. For each of them, a operator has been implemented, which takes this particular type and returns another instance, a reference to the instance of itself. So you can concatenate these operators. And of course, this is technically the bit shift operator, but it also is often used as the append something to a list or output something to a file or to the console operator. So some of the operators are customary to be used for something else, but of course this could have been also just a plus equals operator or something, or plus operator. It doesn't, the language, the C++ compiler doesn't care, but of course it is reasonable to keep to standards so that your code remains nicely readable. Okay, so this much to the output. Of course, as I said, the newer versions of the STL would also allow you to read and write files, but this is not something we'll be looking into today. Since we are already past half of the lecture, we should hurry up with the other mostly useful types. So we will be just for now replicating a few of the types that we have already kind of built ourselves. So for example, a vector. Std vector, let's say of something int, is like our my array that we have created. It creates one block of memory which contains all the elements, but it is self-growing. So our array required us to specify a size, and it's stuck to it. The vector, my vector. Here we can just push back values as we want. Let's do a for loop. Push back I, and it will just be growing the thing as we need it. It also has a reserve function. So if we know roughly how many elements we want to put into our vector, then we can tell it to our vector, and then it will consume all the memory from the get-go. But unlike a normal array, if we then add an 11th and 12th, actually the continuation is 10 and 11. So and 10 and because like we have at 0, so there's so the first element is 0 and so on. So the 11th element is 10 and the 12th element is 11 and so on. So we can add them and it will not crash because the thing will see, well, I need more memory, so I will reallocate it. Not doing this will only have an impact on performance, not on security, because every operation where the vector grows needs all the old elements to be copied to the new memory block. And given that the vector may also hold not just integers, which can be just copied in bulk with a memcopy, the vector could hold, for example, a string, which you cannot memcopy. The string, for the string, you need to execute its assignment or its construction operator, copy construct, I mean, such that it will internally create something else. And for this to improve the performance of this, they are sometimes using specially implemented move instructions, but this complicates things, so we will not be looking into that. The idea generally is that since this vector can really hold anything, it will create a new object, and it will make assignment from each old object to the new object, resulting in duplication of a lot of data and a lot of operations potentially. Thus, if you know how many elements you will need, you will get a much better performance with pre-allocating the right amount of elements. Some of this type of containers, the way they work is when they see that you are growing them like one by one, is that they will try to anticipate how much more space you might need and like they will always grow, let's say by 10% or grow by half of their old size, or another approach is just to double the size each time it needs to grow. So you would grow, well, by 1 on the first insertion, you will grow by 2 on the second insertion, but then the third insertion is already free, the fourth as well. I think I'm off by 1, but doesn't matter. The idea is that then on the next insertion you would then grow by 4, so you would have 3 free insertions, and so on and so on. So it will try to intelligently avoid copying too many things when it's not necessary. And of course you also have a size function that can give you the size, so it just returns you how many elements you have. So we could std say out we have space elements and see std what was it, there was some placeholder for a new line. Doesn't matter, we can just use \n for a new line. But there is some defined value on in the std library that holds like the platform-specific line termination. So on Windows \r\n, although Windows works nowadays perfectly fine with just \n, or just \n as is the Linux standard. Since we are here on Windows, let's do it correctly. So this, let's quickly run it, of course. Recently we didn't run that many things. Wait, that is... we have this thing. Oh, I have a typo. Our loop never terminates. Oops. How did that happen? Yeah, and we have elements. We forgot here, of course, to write \r\n. But as you see, it works as expected. And the nice thing is that if you have, for example, some Windows API that tells you it wants a buffer, it wants something that you malloced, basically. But you want to kind of use modern C++ and be able to use exceptions and memory be deallocated automatically. You could, of course, have something that will hold for you a buffer, some sort of smart pointer, but a very commonly used thing would be that you just create a vector of, for example, char by and then if we have a function, let's say, yes, it's not a Windows function, but it's a function that wants basically just a buffer. Then you can get data, and it will just give you the pointer, the first element. What else? This is the sprintfs. That thing should want to have the count, yeah. And you can get size, and size here means always in the yeah, that will crash. Size always means size in a count of elements. So this is something I don't like about the STL, that they always use size, even with things that so I would ideally want size to always mean size in bytes. And if you have a string, you would use length, although for strings they have length. However, they have both. They have size and they have length, but it is always effectively length. So if you have a v string, a wide string, it will not give you the size in bytes. You will need to multiply it by the size of one character. And of course here, when you have a vector of ints, it will only give you the count, i.e. 10, or in this case 12, and not the actual amount of memory allocated. So ideally, if one would develop such a framework from scratch, one would make strings, for example, only have length, or have length in size, but size meaning size in bytes, and a vector and other similar types being size in bytes and count as a count of elements. But here size is always the count of elements, so this is something to remember. But of course, if we take char, then it is the right amount. But the bug here, why this would crash, is because the thing is still empty. So we would need in this case to either reserve or resize it. So there is actually a subtle difference between reserve and resize. Reserve grows the internal buffer. So there are two attributes actually to a vector. You have its size, or count of elements, and its capacity. The size is how many elements are actually there, actually used, and capacity is how much would fit into the currently allocated memory. And resize, what it does is it sets really the size to the used size. So if you query size, you will get this value, while a reserve will only reserve this amount of elements. And there might also be differences with regard whether resize will initialize the memory or not. So, for example, what you would do is here we know we need 5 characters, so we would or we can, for example, resize it to something larger, like let's say 10, and our sprintf should give us int count the amount of characters does it wrote. So then we would make another resize to truncate it back to the size that we actually have used. And now we could print this, for example, 1 by 1. But for now, let's not do that. Let's just run it. Oops, I need that breakpoint. And see it in the debugger. So we see here we have test. Then we have the 0 character, and it still has some elements reserved. And you also see here. It didn't work. Oh wait, I used reserve will not truncate anything. So if you try to reserve less than what you have, then it will just don't do anything. That was a typo. Okay, now it's correct. But you see, a capacity is still 10, and in principle there is more memory allocated. We just don't see it here because the IntelliSense uses the size value to display the element count. Okay, so far everything clear? Okay. If everything seems clear, then let's continue. So one thing that you can do with pretty much any container type in STL is you can iterate through it. So obviously with a vector, the vector will implement for int e equals 0 is less than size e plus plus, and we can of course let's say f test1 backslash n, then we just will print f %c the individual characters from our buffer, and we can access them like in an array with their index. And when we are done, we'll just backslash n. So let's see. Okay, works as expected. Test one test. Actually, maybe not want the other. This backslash even. And this works. And but this method works only with vector and array. There is a std array, but it's just fixed size, and it's just a wrapper so that you can use other STL constructs on a fixed memory block. But usually you would use this vector. And there is another way to go through a container type, which works on any type. And of course, square bracket also works on string. But for example, if you would have a list or a map or something other, then it wouldn't work. And the way you usually go through is you are using a mechanism called an iterator. So let's make an example for and now the ugly side of of STL. With STL, when you're using STL a lot, you will get extremely long types, which is extremely not user friendly. So you should try always, whenever possible, to type these things, which will cut down on the length of your types. So we pretty much have an object called an iterator, which is defined on any of those of our instances. We usually call it I, and we can assign the begin of our vector to it, and then we can iterate through it as long as I is not the end of our vector. And to iterate through it, we just plus it. Oops. And usually both work. The customary way is this, and only this one is the one which is required on an iterator to be implemented. So if you would implement your own iterator, this must work, while this might not work. Historic reasons. And of course here we then work similarly. Test2. Zack, zack. Just that now we have our iterator, and the iterator has a asterisk operator implemented. So the iterator is like an object, to some extent like a sort of smart pointer. And as you remember with our old smart pointer here somewhere, we have implemented. We didn't have implemented it? No, must have. Yeah, here. We implemented our asterisk operator, and the same way here they have implemented an asterisk operator which then unwraps the internally referenced value, in this case the character which we have written. So when you run it again, we'll just get test1 and test2 giving us the same result. But this mechanism now could also be used, for example, with a linked list, which brings us to something that will become a homework today. As you know, you have your linked list on which you are working, making it C++. The assignment, but we will specify it a bit later, will be to add an iterator to it. And with more modern versions of C++, this rather ugly and cumbersome construct has been replaced with a thing called a ranged loop. And also we don't need to use this super ugly, super long thingies. We can just use a auto keyword, auto c, let's call it, because it will be a character, a double point container type, and then voila, we can just do it directly. So this is much nicer, obviously. And since we actually know that this is a char, we could also write a char. And what we also could do, in fact, is here we could of course replace this with auto, what we want. So auto is a placeholder for whenever a type can be inferred by the compiler. In modern versions of C++, you can just use auto and it will just figure out which type there should be on its own. And it's quite useful. And of course, such an approach is even nicer because then you have even less writing of code. And it does internally under the hood the exact same thing. It will make a call to begin, it will get an iterator object, it will plus that iterator, it will compare it with the end, and when it's done, it's done. So when you will be implementing this with a simple object, then you can step through it and take a look that really those two things under the hood work very similarly. Okay, so one thing, of course, you might also want to do is you might want to remove something. So let's maybe do it here. So what you can do is, if you have your iterator, if you can plus it, let's say you can plus it twice. This will give you the iterator pointing to the S letter in our test. And it's not this S letter here. And what you can do is you can just erase. So there is a function called erase which takes an iterator, and what it does is, in fact, it returns an iterator to the next element in the element. So in the map or in the list or in the vector or whatever you have, which also is quite useful. We will see it shortly why. But here, as you see, we could just explicitly delete the S character. With the string as such, we saw here we could also use erase with just specifying the range and the offsets. But such a thing is not necessarily available on all of the things. So here this one takes an iterator or like two iterators. So you could have a range like a begin and end iterator, and you want to erase everything in between, then you can do it. But on the vector already you cannot operate with indices. So indices, like also the substring, which where was it? Here, which just gives us a portion of a string. Those things only work on strings, even though you could in principle want such behavior also on arrays or vectors, but STL has not implemented that. They don't need it for strings. And why it is useful that the arrays returns you an iterator when you're in a loop, for example. Let's quickly do it here. Let's make an example. So we copy this. This time we use the auto keyword just for demonstration purposes. And let's not plus plus here, but plus plus manually here. Let's say we want to remove all the letters T from our test string. So if asterisk E is equals T, then E is equals arrays. E is equals my buffer arrays E, or else we need to advance to the next element. So we start with the begin. We check if it's T. If it is T, we erase it and we get the iterate at the next element. Then we check whether it's null. Not null. We check whether it's the end, because it might be. If it is, then we break. If it's not, then we continue. Then we check again, is it T? If it's not T, we go here. We increment. We check. We test. We increment. We test. We check again. The last T is then again erased. Then we check here, and it's null, so we are done. And of course, if we copy this line, if we move those lines, we will see now, of course, that content of our buffer being altered in the correct way. The T's have been removed. And yeah, that's that much the vector. Let's quickly take a look on the other container types which one might use. So, for example, here the list, which we need to include because we haven't done this yet. So here it behaves kind of the same way, but when we try this, so I should change the names. That's not correct. Vector, now it's our list. Now, as you see, we don't have reserve on list, which already gives us a hint. The list does not store its entries in a consecutive memory range. The list creates a new entry for a new memory block for every entry, meaning we can super cheaply append elements on the beginning and the end, and if we want to access something in the middle of the list, we have a problem. Although the iterators help with that as well. So we have our list. Here again, this thing complains there is no square bracket operator on a list because it can't be. It doesn't have any means to find an element somewhere inside. Now there are other languages which kind of try to enable this, or you could write your own list implementation in C which would enable this as well, which would basically be an optimization for the case where creating and copying of your elements is very expensive, where you don't need actually consecutive memory as we actually need it in the printf example, but where you want to be able to access elements by index. What you would then do is you would have basically a vector or an array of pointers to all the elements in your linked list, and whenever you add an element, you would potentially need to shift, grow, or truncate your vector, and this would allow you to access them by index, but at the expense that you have additional operations with every append or remove operation on your list. So depending on what you want to achieve, this might be a worthwhile optimization, or it might just add unnecessary computation. So here for the list, as we see, as mentioned, we cannot do that, but what we can do is we can just print it the old way with the iterators, because the iterator goes like from one entry to the next, to the next, to the next, and the same way we printed things with our linked list when we implemented that. Let's go with auto. The same way here, the iterator, so the list knows where its head is. When you make begin, then it will give you the begin. If you want the end, it will give you the end. Although end is like not the last element, but end is like the element after the last element, which by definition always is invalid. So it's not quite the tail of the list, because like on a normal linked list, the head and the tail, if the list has, for example, one element, the head and the tail both point to it. Here it's explicitly differently. Begin and end are only then equal if the list is fully empty, if there are no valid elements inside. Same for vector or any other container type in STL. But as said, you still have here the asterisk operator, so you can get your value if you would run it. We would this is not quite right, because we want, of course, we have integers in this list, not characters. So if we want to print this, now we have printed them. Maybe should want to add spaces so that the 0 and the 10 don't get mixed up. Zack. But as you see, it works. And of course you can use arrays. You can also use insert, for example. So list insert, and then it asks you for an iterator. So if you would be going through a list and you're trying to sort it, you can work with arrays, insert. There's usually also a swap implemented, which just takes okay, this swap does a different thing. It swaps with two lists, the contents of two lists. But you could have a swap operation or a swap function on your list, etc. Whatever you want to implement, you can. And when you're using STL, then as said, you can use arrays and insert to move elements inside your list and stuff like that. You just need to keep track of the iterators. And the very important note is that as soon as you add an element to a list or remove an element from the list, by definition, all the iterators to this list become invalid. So that is why the arrays operation gives you a new iterator as a return value. Actually, insert. I think for insert it is. And insert, as you see, it also gives you here an iterator. In practice, you would see that you're depending on what you are working with. So if you have a vector, an insert or an arrays usually doesn't, but an insert may always trigger a grow. And as soon as you have a grow, then all the other addresses that you have obtained for this vector are invalid. And with lists, the practical case is that if you have iterators like from the ends and you do something in the middle, or well, if you're doing it not exactly on the iterator or something which is neighbored to the element you are working with, then usually they will stay valid. But relying on such things might not be recommended. So whenever you insert or remove something from a list or a map or a vector, you should just assume the iterators to have become invalid and only use the iterator that you got back from the erase or the insert function, because those are guaranteed to be valid because they are new, they have been newly created, such that they will work with your particular new content of whatever your list contains. And the last two things which I want to show you today is the map and the unsorted map, or rather unordered map. And strangely enough, they changed this because a long time ago this was just called a hash, short for hash table. But since it was kind of ambiguous from the name, they changed it to unordered map. And now if you have old code which used hash tables, then it breaks. The idea of such a so from your perspective, map and unordered map work quite similarly. You can have anything as key within certain constraints, and then you can have really anything as value, and it allows you to store values under those keys and retrieve them. So you can look things up, and you can also iterate through the whole thing. The main difference is that the unordered map requires whatever type you want to use as key to be hashable and to have a equals operator, while things that you put in the ordered map only require to have a less than operator. So let's quickly start with it. Std map std string, string std that's int, and my map for int e is less than 10 e plus plus. And let's add something. So for the map, we use the square bracket operator usually, and std into string from e. So this will give us a string interpretation of e, and we can assign some value we want to assign to it. and later if we want to get something out, so for example int 10 is equals map. 10 is too much, too little. Let's go with let's go to 20 here, or to 100 entries. Map from 10, and it will give us now the number 10, which was stored under this entry. The thing is, if we want 1000, it will give us 0 because we haven't stored 1000, but it will give us the default value for whatever type there is, and more than that, it will actually add this entry with the initialized value to the map. So if we would print the map after we did this, it will print us the additional the 1000 entry as well, because it added it, even though we didn't want that to happen. So maps in this sense are a bit worrisome. You need to be careful, but of course if you want to find if something is in a map, you can, and something that might not be in a map, then you can use the iterators. Auto e is equals auto is equals map punct find, and then we specify the key, and find will give us end of map if it is not contained. So if let's so if I is not equals map and so let's make an integer int. We don't know it, so we start with 1000, and then it's equal. So if it is not n, then it is equals I, but unfortunately we cannot use the asterisk operator. We have to wait. I'm missing the equal sign. But we have to use the dot the arrow second. So the map contains always a pair of values, basically like the key and the value. And the way the first maps for the steel were implemented is that the iterator gives you pretty much a pointer to this pair of values, instead of giving you just the value without the key, which is, depending on what you want to do, kind of nice, because if you have a if you want to print your map, we start with auto, we just go here with my map, then you can so you cannot asterisk I, but you can first, comma I second. First was a C string, so to print this we need C sharp, so we have %s Doppelpunkt %e Strichpunkt Abstand. Yeah, and we have a few too many test 3s, test 4, test 5. So when we do it like this, we can find out which keys and which values are stored in the map, which is very useful. Other frameworks, like for example the Qt framework, chose to solve this differently. In a QMap, you have the asterisk operator on the iterator, and it just gives you only the value. But they implemented on your iterator just a couple of other functions, like a dot key or dot value, which, well, value is redundant with using the asterisk on e, but dot key will give you the key under which this value is stored, which is quite nice, and I actually prefer the way Qt made it, because it's easier to read text, because here you always need to remember first is the key, second is the value, and it's kind of not super readable code. They could have at least take a type where one is called key and the other is called value, but they kind of wanted to be smart, and they just use a generic std pair structure, which is quite nice in the sense that it allows you to easily return, like for example, two values. But using this as your primary data storage for your map is not elegant. Let's just say it is not elegant. And of course, the unsorted map would kind of behave very similarly. Let's quickly do that. And also, let's go only to 10, and let's comment this out, and let's call this 9. Yeah, that is a good 10. This is then 1000, right? So we copy everything, I'll just rename this my UMAP. Okay, now let's print it. Now we have twice. Let's get rid of that. And we have 2 9s. Let's go with 8. Oh, it's for 2. Let's go with 2. Okay, and when we see here, we see that they ended up being sorted as well. That is... Oh no, I didn't change it. Of course, need to change the type here. It was suspiciously sorted. Yeah. Still ended up sorted. So the unordered map should in principle be unordered, but of course there might be some internal order to the thing. This is annoying. That is really how can we break that to demonstrate it properly? Let's say so what it does is it will be hashing those values. It keeps the order. Generally, the way, at least according to specification, is that you cannot rely on the unordered map to have any particular order, but apparently here we end up with having some sort of order, which for some reason is the natural one. We can try, of course, swapping here the values. Because the way they are in terms... wait, what? E? E comma, it should not complain, but it comes. But it complains. And we are running out of time, so we need to speed up with that. Second, first, okay, let's do it like this. We swap this once. Second, yes, no, it's fine. Right, and here we of course changed, so we have to comment this out. No, it still is sorted. Well, it's annoying. Generally, the way this works, I said, is that this thing will create hash values and then store the data in a array internally, where these hash values are the indexes for this array. And each entry might have, each bucket might have more than one entry, but usually it doesn't. But here apparently, for some reason, this does not demonstrate the right behavior. We don't see those things being this unorderly, and I'm not quite sure why this is, because I said the definition of the unordered map is that it is a hash tree and that should be not ordered. So apparently just the hash function which they're using, when we just feed it numbers, sequential numbers, generates indices which are also sequential. So we would need to find some more complex example to demonstrate this. So for now we won't do that. Let's just leave it at this. And since we only have 10 minutes left, let's take a look to the homework assignment. So we will open our CPP list. Right, and just one more comment about this. We will continue looking into the use cases for the different container types and into other things like STL provided smart pointers and so on during the next lecture. So here we just started, but we will continue. So we will learn more about those containers and how you can use them. Just that since now we are running out of time, we need to switch to the next assignment. So homework from the, what's today, 15th? Oops. Add to the list. Begin, enter, erase, and insert. This is the lowest common denominator. Okay. Yeah, and we are already running out of lectures because, as far as I saw, the next month there will be 2 holidays, so we only have 3 more lectures to go. So the plan for the next lectures will be during the next lecture you will get your final assignment, so the final project that you will have to finish to the end of next month. And in the during the next lecture we'll continue on the STL stuff and iterators and so on and so on. And during the last 2 lectures in the semester we'll take a look on interacting with C++ objects from C alone. And if we have enough time, then we'll also take a look on some more funny things with low-level manipulation of code in memory and stuff like that. So this is just this will be more for your entertainment. It will not be subject of any homework or so on. It will be just something that is good to have seen and to have experienced at least once, even although you might not necessarily need this in your everyday work. So this is a more advanced thing, but since this is a low-level class, I think it is good to demonstrate those things because this gives you quite a good feeling and understanding how direct your access to the hardware is when using C++ over other languages where you couldn't do such things. Do you have any questions? No questions? Okay. Then I would say it's a good point to finish for today. And as said, next week we continue with all these nice standard template thingies. Maybe quickly want to write down what we'll take a look at. Multimaps. A multimap is like a normal map, just that it allows you to hold more than one value under the same key. Then more maps is quite also interesting because you can do more things with maps than just what we have seen here. You have an insert function, which, for example, it tells you whether a value in the map was overwritten or a new value was added, which is kind of nicer than using the square bracket operator because it gives you more control. There are on the sorted maps the upper and lower bound functions, which are also quite helpful because this way you can find something even if you don't know the exact key. You will find the thing with the closest key to what we were looking for, which in many cases might be a very useful mechanism. Then of course smart pointers, and we might want to take a look on multi-threading if we have enough time. Okay, so see you next week and have a nice evening. Bye bye.